Okay, so let's start with our first speaker. We have Rita Neves from Madrid, and she's going to tell us about, loop quantum cosmology.
Yes, thank you. Okay, so I'm going to tell you about loop quantum cosmology, more particularly about some anomalies that we can alleviate in a particular model of loop quantum cosmology. And this is a work I've done in collaboration with my supervisors, Mercedes Martin Benito and Javier Olmedo. So for anyone who is not familiar, loop quantum cosmology is a particular approach to quantum cosmology that is based on techniques of loop quantum gravity. So it applies these techniques to cosmological models. And the most important result that is relevant for my talk today is that of the Big Bang singularity that is resolved in terms of a quantum bounce. So we have a positive minimum for the volume. And we have a contracting epoch of the universe connected to an expanding one. And this means that the energy density is finite, it doesn't diverge. And more importantly, it means that we have well-defined pre-inflationary dynamics. And this can affect cosmological perturbations, and this can excite them and leave imprints in observations. So concretely, what we mean is that in standard cosmology, usually we study cosmological perturbations by fixing the vacuum at the onset of inflation, because we have the singularity shortly before. And then once we fix the vacuum, we can evolve them. We see that they oscillate while they're inside the horizon, and then they freeze. But in quantum cosmology, we have things happening before the onset of inflation. The background has non-trivial dynamics. And the idea is that these non-trivial dynamics can influence the evolution of perturbations. They can cross out of the horizon and back in all before the inflation begins. And so the different background affects the dynamic of perturbations. And on top of that, we also have corrections to the equations of motion that look something like this, the corrections that come from the quantum dynamics. So all of this is to say that the effects coming from loop quantum cosmology can have visible effects in the primordial power spectrum, which is just a power spectrum at the end of inflation. So the primordial power spectrum, the particular shape, the concrete shape of the primordial power spectrum depends on the choice of vacuum. But in any scenario, it will be, in the ultraviolet, it will agree exactly with the power spectrum of standard cosmology, which is a near scale invariant power spectrum. And so the departures will be in the infrared, so below a given scale, a characteristic scale of the model. And then the question becomes whether these effects are within the observable window, or whether the bit that we observed is indistinguishable from the standard model. And this is related to parameters of the theory that makes us have more or less inflation. If we have too much inflation, everything stretches out too much, then the effects become too infrared and they are not observable. So the vacuum that we choose in this work in particular is called the non-oscillatory vacuum. It's a vacuum that, by construction, it minimizes oscillations of the perturbations in time, and this results in a minimization of these oscillations in the primordial power spectrum. And the motivation behind this is that these oscillations that could show up otherwise kind of spoil the effects that are coming from the bounce. This is something that has been well motivated in the literature. And also, it gives us a pretty simple power spectrum. We just, essentially, the main feature is a power suppression in infrared modes. And this is an interesting one to study also because many power spectra from loop quantum cosmology have some sort of power suppression for infrared modes. So we can learn something about those as well by studying this one. So what we do is to parameterize this power spectrum. We have a fixed slope of the suppression here. We also have a fixed amplitude of the oscillations. This doesn't change with the parameters of our theory. The only thing that changes, besides the things that relate to the near-scale invariant part, which is already in the standard model, the only thing that changes is this parameter, the scale at which the suppression occurs, essentially. So this is going to be our parameter, and it's related to how much inflation we have. If we have too much inflation, this becomes very infrared. If you have less inflation, this becomes more ultraviolet. So we take this power spectrum, we parameterize it, and we leave this parameter free, along with all the parameters of lambda CDM, and we perform a Bayesian analysis. So we're going to look in particular at this parameter Kc, which is the one that gives us information about loop quantum cosmology. And what I'm showing here is what is called the posterior probability of the parameter. This is just the probability distribution of our parameter given the data of the CMB in this case. So a peak in this distribution tells us the value of this parameter for which our model best fits our theory. So you can see that we have a region here with a plateau. This is just values of Kc that are not within the observable window. So any value here will give us exactly the same observable part of the power spectrum, which is the same as the standard model. Then we see that we have a peak here, which is within the observable window, which tells us that the data prefers some of the suppression to be observable. And then we have a sharp cutoff that tells us that it can't be too high. We can't have too much suppression. That will not agree well with the data. But still, we can see that some effects are preferred by the data to be within the observable window. So we want to see what happens with some anomalies that have been identified in the data. These are just tensions between the data and predictions of the standard model. Okay, so the first anomaly is the lensing anomaly. This came up as a consistency check within the standard model. Essentially what it is that we put by hand a parameter that is called the lensing parameter, this AL, this lensing amplitude. And what it does is change how much the CMB is lensed from the surface of last scattering until today in its path. But it's not something predicted by the theory. It's a phenomenological parameter. And the consistency check is to allow this parameter to vary with all the other parameters of a theory and look for its posterior probability. And what you see is that the data prefers this value to be different than what lambda CDM would predict, which is 1, would be consistent with lambda CDM. Okay, so there's some inconsistency here at the level of 2 sigma, and it's even more than that, because then if you allow the curvature of the universe to vary, you can see that whatever inconsistencies are being measured by this parameter can disappear, which means that this can be 1 reasonably when comparing to the data, which means that it's within the 1 sigma region that I'm showing here in this 2D distribution, as long as the curvature of the universe is negative, which means it's a closed universe. But then this leads to inconsistencies with other sorts of data, and this has been labeled a crisis in cosmology, and it's an anomaly that people have been looking at from various approaches. So one of the approaches that can help alleviate this is loop quantum cosmology. And what happens is that loop quantum cosmology, with all these effects that show up in the power spectrum, and it does affect the distribution of other parameters, not just Kc. One of them is this tau. This is the optical depth at ionization. These are parameters that are relevant for the universe after inflation. But it changes the statistics enough that the predictions for this parameter are shifted. And this parameter is anti-correlated with our lensing amplitude. So what happens with loop quantum cosmology is that as we introduce more and more power suppression in the power spectrum, this ellipse, this projection of the posterior, kind of shifts so that this amplitude can be more consistent with 1. And what happens is that the constraints for this parameter are going to be shifted to higher values. This is okay because this parameter is the one that's less constrained from observations. And it also tells us that future observations, independent observations of this parameter, can help us constrain Kc and effectively constrain how much we can allow the model to have these effects in the primordial power spectrum. So the second anomaly. Okay, so the second anomaly that I'm going to talk about is the power suppression anomaly, and this is the fact that the angular correlations are consistent with 0 for large angles. This is what I'm showing here in the black dots is the data, so you can see they dance around 0 from like 60 degrees onwards, and this is measured by this estimator, which is it's just an integral of the square of this quantity for large angles. You can see that the prediction formula on the CDM, so it's in some parts is very inconsistent with that. Concretely, this estimator is around 35,000 in the standard model, and the measurement of the data is 1,200. So this means that our realization of this universe, the one we're observing, seems like a very unlikely realization of the model. But to know how unlikely, we need to study the p-values, so the distribution of this estimator. And this is what we do, I hope. No, yeah, this always happens to me. Can I? No. Did I do something?
Can you check?
Where do I have to point?
It's on this side.
Okay.
I think it works now if you plug it in.
Thank you. Okay, sorry. So this distribution, we study the distribution of this parameter. So what that means is we take our model, we do many realizations, and we do a histogram. So the p-value will be the fraction of realizations that have an observed an estimator that is at least as small as the observed value, which is this line here. So you can see it's the very, very end of the tail of the distribution. And this is actually corresponds to a very low p-value. And what happens in our model is that this distribution is shifted to lower values. And so the portion of realizations that have this value for S1/2, the observed one, is larger. And it's in this sense that we alleviate the anomaly. And so finally, just to finish, we also looked at the parity asymmetry anomaly. And this is the fact that the data shows that there is more power in odd multiples than in even ones, which you can see through this estimator. So if this is smaller than 1, then there's more power in odd multiples. Lambda CDM does not predict any asymmetry at all. And you can see for lower multiples, we have very, very low p-values in lambda CDM. In this case, in our model, even though the expectation value does shift slightly to levels below 1, as you can see in the red line here, you can also tell that the 1 and 2 sigma regions shrink for most values. And so we can't really tell here, but this essentially means that we haven't alleviated the anomaly. And we can see this more accurately what is happening if we plot one of the distributions for one particular L max. And what is happening is that even though the maximum of these distributions shifts slightly, it's also getting thinner. So essentially, the portion of realizations that correspond to this universe we are observing actually gets smaller. And this is for one particular value. For others, it gets slightly larger, as you can see for these ones here. But what we can say is that power suppression alone in the power spectrum is not capable of alleviating this anomaly. So, just to finish, we have seen that loop quantum cosmology can have observable effects in the power spectrum, and it will be in the infrared, and that the data hints at a preference for some power suppression in the infrared to be within the observable window. This can help alleviate some anomalies, the power suppression and the lensing anomaly that I showed. But for the parity anomaly, we need to study more features in the power spectra. And in particular, it has been shown that power enhancement can be relevant for this anomaly to be alleviated. And this is something you can also obtain in loop quantum cosmology with other choices of vacuum. And it's what we want to do in the future. So thank you.
Thank you. Are there any questions? Well, I can start. So you said that you're choosing this non-oscillatory vacuum. So, well, how do you choose this vacuum, and how dependent on this choice are your results?
The primordial power spectrum depends a lot on the choice of vacuum. As I said in one of the slides, many of the choices of vacuum within local quantum cosmology lead to some power suppression in the infrared, most of the ones that I've seen, but some also have power enhancement and oscillations. So in that sense, it depends a lot on the choice of vacuum. And this vacuum is chosen, it's constructed numerically by minimizing the oscillations of the perturbations from the bounce to the onset of inflation by hand. So you minimize this quantity. It's numerical. And this leads to a minimization of the oscillations that you would otherwise see in the power spectrum.
Okay.
But the results depend a lot on, of course, on the choice of vacuum.
And you have a bounce for this?
Yes.
Yep. Yes, it's working.
So following on from the last question, with these vacuum states, I guess you'd want it to have something like a Hadamard type property.
Yes, we have shown that this vacuum is Hadamard.
Really? So it's like a construction of a Hadamard vacuum state.
Yes. When it was first introduced, it wasn't explicitly shown that it was Hadamard. It was numerical. You could tell that it was most likely Hadamard. We have shown in a paper that it is by comparing it with another vacuum, which is shown analytically to be a Hadamard. So we compared the ultraviolet expansion of them, and we find that they're the same.
So you have an analytic handle. It's not just numerical, is what you're saying?
No. In our work, we did everything numerically, but there are works where this is handled analytically as well.
Thank you very much.
Okay, thank you. Let's thank our speaker again.